Hi everyone, I am Sham Parik. I am a student of BSc Chemistry Honours second year. My roll number is 10 and today we are going to discuss the chapter Chemical Kinetics. Chemistry by its very nature is concerned with change. Substances with well-defined properties are converted by chemical reactions into other substances with different properties. For any chemical reaction, chemists try to find out A. The feasibility of a chemical reaction, which can be predicted by thermodynamics, as you know that a reaction with delta G greater than 0 at constant temperature and pressure is feasible. Extent to which a reaction will proceed and can be determined from chemical equilibrium. Speed of reaction, that is time taken by reaction to reach equilibrium. Along with feasibility and extent, it is equally important to know the rate. It is important to know the rate and the factors controlling the rate of reaction for its complete understanding. For example, which parameters determine as to how rapidly food gets spoiled, how to design a rapidly setting material for dental filling, or what controls the rate at which fuel burns in an auto engine. All these equations can be answered by the branch of chemistry which deals with the study of reaction rates and their mechanism called chemical kinetics. The word kinetics is derived from the Greek word kinesis, meaning movement. Thermodynamics tell only about the feasibility of a reaction, whereas chemical kinetics tells about the rate of reaction. For example, thermodynamic data indicate the diamond shall convert to graphite, but in reality the conversion rate is so slow that the change is not predictable at all. Therefore, most people think the diamond is forever. Kinetic studies not only help us to determine the speed or rate of chemical reaction, but also describe the condition by which the reaction rate can be altered. The factors such as concentration, temperature, pressure, and catalyst affect the rate of a reaction. At the macroscopic level, we are interested in amount reacted or formed and the rates of their consumption or formation. At the molecular level, the reaction mechanisms involving orientation and energy of molecules undergoing collisions are discussed. In this unit, we shall be dealing with average and instantaneous rate of reaction and the factors affecting these. Some elementary ideas about the collision theory of reaction rates are also given. However, in order to understand all this, let us first learn about the reaction rates. Some reactions such as ionic reactions occur very fast. For example, precipitation of silver chloride occurs instantaneously by mixing of aqueous solution of silver nitrate and sodium chloride. On the other hand, some reactions are very slow. For example, rusting of iron in the presence of air and moisture. Also, there are reactions like inversion of cane sugar and hydrolysis of starch, which proceed with a moderate speed. Can you think of more examples from each category? You must be knowing that speed of an automobile is expressed in terms of change in the position or distance covered by it in a certain period of time. Similarly, the speed of reaction or the rate of a reaction can be defined as the change in concentration of a reactant or product in unit time. To be more specific, it can be expressed in terms of the rate of decrease in concentration of any one of the reactant or the rate of increase in concentration of any one of the product. Consider a hypothetical reaction assuming that the volume of the system remains constant. Reactant gives product. 1 mole of the reactant R produces 1 mole of the product P. If R1 and P1 are the concentration of R and P respectively at time T1 and R2 and P2 are the concentration at time T2, then delta T equals to T2 minus T1 and delta R equals to R2 minus R1 and delta P equals to P2 minus P1. The square bracket in the above reaction are used to express molar concentration. So rate of disappearance of R equals to decrease in concentration of R by time taken, which equals to minus of delta R upon delta T. And similarly, rate of appearance of P equals to increase in concentration of P divided by time taken, which is equal to plus of delta P upon delta T. Since delta R is a negative quantity as concentration of reactant is decreasing, it is multiplied with minus 1 to make the rate of reaction a positive quantity. And these equations give above represent the average rate of reaction R average. Average rate depends upon the change in concentration of reactants or product and the time taken for the change to occur. Units of rate of a reaction. From equation 4.1 and 4.2, it is clear that units of rate are concentration time inverse. For example, if concentration is in mole liter inverse and time is in second, then the unit will be mole liter inverse second inverse. However, in gaseous reaction, when the concentration of gases is expressed in terms of their partial pressure, then the units of the rate equation will be atm second inverse. Now we shall discuss about average rates of hydrolysis of butyl chloride C4H9Cl at T1 and the units is mole liter inverse. It is 0.100, 0.0905, 0.8200, 0.0741, 0.067, and so on. It can be seen that the average rate fall from 1.90 into 10 raised to the power minus 4 mole liter inverse second inverse to 0.4 into 10 raised to the power minus 4 mole liter inverse second inverse. However, average rate cannot be used to predict the rate of reaction at a particular instant, as it would be constant for the time interval for which it is calculated. So, to express the rate at a particular moment of time, we determine the instantaneous rate. It is obtained when we consider the average rate at the smallest time interval, say dt. That is when delta t approaches 0. Hence, mathematically, for an infinitesimally small dt, instantaneous rate is given by r average equals to minus delta r upon delta t equals to delta p upon delta t as t tends to 0, or r instantaneous equals to minus delta r dt, delta r dr dt, or dp upon dt. It can be determined graphically by drawing a tangent at time t on either of the curves for concentration of r and p versus time t and calculating its slope. So in problem 3.1, r instantaneous at 600 seconds, for example, can be calculated by plotting concentration of butyl chloride as a function of time. A tangent is drawn that touches the curve at t equal to 600 seconds. The slope of this tangent given the instantaneous rate. So r instantaneous at 600 seconds will be 0.0165 minus 0.037 equals by divided by 800 minus 400 second mole liter inverse, which is equal to 5.12 into 10 raised to the power minus 5 mole liter inverse second inverse. At t equals to 250 second, our instantaneous will be 1.22 into 10 raised to power 4 mole liter inverse second inverse. At t equals to 350, rate will be 1.0 into 10 raised to power minus 4 mole liter inverse second inverse. And at t equals 450 second, rate will be instantaneous rate will be 6.4 into 10 raised to power minus 5 mole liter inverse second inverse. Now consider the equation Hg at liquid plus Cl2 gives us HgCl2. When stoichiometric coefficients of the reactant and products are same, then rate of reaction is given by rate of reaction equals to minus delta Hg upon delta T equals to minus delta Cl2 upon delta T equals to delta HgCl2 upon delta T. That is, rate of disappearance of any of the reactants is same as the rate of appearance of the product. But in the following reactions, 2 mole of Hi decomposes to produce 1 mole each of H2 and I2. 2Hi equals to H2 plus I2. For expressing the rate of such a reaction where stoichiometric coefficient of reactant or products are not equal to 1, rate of disappearance of any of the reactant of the rate of appearance of product is divided by the respective stoichiometric coefficient. Since rate of consumption of Hi is twice the rate of formation of H2 or I2, to make them equal, the term delta Hi is divided by 2. The rate of this reaction is given by rate of reaction equal to minus 1 upon 2 delta Hi upon delta T equals to delta H2 upon delta T equals to delta I2 upon delta T. Similarly, for the reaction 5Br minus at aqueous form plus BrO3 minus plus 6S positive gives us 3Br2 plus 3H2O. The rate will be minus 1 upon 5 delta Br upon delta T equals to minus delta BrO3 whole minus upon delta T equals to minus 1 upon 6 delta H positive upon delta T is equals to 1 upon 3 delta Br2 upon delta T is equals to 1 upon 3 delta H2 upon delta T. For a gaseous reaction at constant temperature, concentration is directly proportional to the partial pressure of a species, and hence rate can also be expressed as the rate of changing in partial pressure of the reactant or the product. Now there is an example. The decomposition of N2O5 in CCl4 at 318 Kelvin has been studied by monitoring the concentration of N2O5 in the solution. Initially, the concentration of N2O5 is 2.33 mole liter inverse, and after 184 minutes, it is reduced to 2.08 mole liter inverse. The reaction takes place according to the equation 2N2O5 at gas equals to 4NO2 gaseous plus O2 gaseous. Calculate the average rate of this reaction in terms of hours, minutes, and seconds. What is the rate of production of NO2 during this period? Solution. Average rate will be 1 upon 2 minus delta N2O5 upon delta T equals to minus 1 upon 2, which is equal to minus 1 upon 2, and the concentration of N2O5 was at product was 2.08 and at reactant was 2.33 mole liter inverse, and the time was 184 minutes. So it is equal to 6.79 into 10 raised to power mole liter inverse, and when it's minute it is 4.07 into 10 raised to minus 2 mole liter inverse and at hour, and 6.79 into 10 raised to power minus 4 mole liter inverse into 1 minute divided by 60 second, which is equal to 1.13 into 10 raised to power minus 5 mole liter inverse second inverse. It may be remembered that rate equals to 1 upon 4 delta NO2 delta T. So delta NO2 into delta T equals to 6.79 into 10 raised to power minus 4 into 4 mole liter inverse minute inverse. So the rate of delta NO2 will be 2.72 into 10 raised to power minus 3 mole liter inverse minute inverse. Now we shall discuss about the rates, about the factors in influencing rate of reaction. Rate of reaction depends upon the experimental conditions such as concentration of reactant, pressure in case of gases, temperature and catalysts. Dependence on of rate of concentration. The rate of a chemical reaction at a given temperature may depend on the concentration of one or more reactants and products. The representation of rate of reaction in terms of concentration of the reactant is known as rate law. It is also called as rate equation or rate expression. Rate expression and rate constant. The result in table 3.1 clearly shows that rate of reaction decreases with the passage of time as the concentration of reactant decreases. Conversely, rate generally increases when reactant concentration increases, so rate of a reaction depends upon the concentration of reactant. Consider a general equation AA plus BB equals to CC plus DD, where small a, B, C and D are the stoichiometric coefficient of reactant and products. The rate expression for this reaction is directly proportional to a raised to power x and b raised to power y, where exponents x and y may or may not be equal to the stoichiometric coefficient small a and b of the reactants. Above equation can also be written as rate equals to k a raised to power x and b raised to power y, and equals to minus dr upon dt equals to k a raised to power x and b raised to power y. This form of equation is known as differential rate equation, where k is a proportionality constant called rate constant. The equation like this, which relates the rate of reaction to concentration of reactant, is called rate law or rate expression. Thus, rate law is the expression in which reactant rate is given in terms of molar concentration of reactant, with each term raised to some power which may or may not be equal to the stoichiometric coefficient of the reacting species in a balanced chemical equation. For example, 2NO at gaseous plus O2 at gaseous gives us 2NO2 in the gaseous form. We can measure the rate of this reaction as a function of initial concentration, either by keeping the concentration of one of the reactants constant and changing the concentration of the other reactant, or by changing the concentration of both the reactants. The following results are obtained. Table 3.2 initial rate of formation of NO2. Experiment 1, 2, 3, 4 respectively. Initial rate 0.30 and the unit is mole liter inverse. 0.30, 0.60, 0.30 and 0.60. And initial O2 mole liter inverse 0.30, 0.30, 0.60 and 0.60. Now we shall discuss about the initial rate of formation of NO2, which is in mole liter inverse second inverse, which is 0.096, 0.384, 0.192 and 0.768. It is obvious after looking at the results that when the concentration of NO is doubled and that of O2 is kept constant, then the initial rate increases by a factor of 4 from 0.96 to 0.8384 mole liter inverse second inverse. This indicates the rate depends upon the square of concentration of NO. When concentration of NO is kept constant and concentration of O2 is doubled, the rate also gets doubled, indicating the rate depends upon concentration of O2 to the first power. Hence the rate equation for the reaction will be a rate equals to k NO2 raised to the power O2 and O2 raised to the power 1. The differential form of this rate expression is given as minus dr upon dt equals to k NO2 NO raised to the power 2 and O2 raised to the power 1. Now we observe that for this reaction in the rate equation derived from the experimental data, the exponents of the concentration terms are the same as the stoichiometric coefficient in the balanced chemical equation. Some other examples are given below. Reaction CHCl3 plus Cl2 gives us CCl4 plus HCl. And experimental rate expression are rate equals to K CHCl3 and Cl2 raised to the power 1 by 2. And CH3COO C2H5 plus H2O gives us CH3COOH plus C2H5OH, and rate is K equals to CH3COO C2H5 raised to the power 1 and H2O raised to the power 0. In these reactions, the exponents of the concentration terms are not the same as the stoichiometric coefficients. Thus, we can say that rate law for any reaction cannot be predicted by merely looking at the balanced chemical equation, that is theoretically, but must be determined experimentally. Order of a reaction. In the rate equation, rate equals to k, a raised to power x and b raised to power y. X and y indicate how sensitive the rate is to the change in concentration of a and b. Some of these experiments, that is x plus y, gives the overall order of reaction, when x and y represent the order with respect to the reaction a and b respectively. Hence, the sum of power of the concentration of the reactant in the rate law expression is called order of that chemical reaction. Order of a reaction can be 0, 1, 2, and 3, and even a fraction. A zero order reaction means that the rate of reaction is independent of the concentration of reactants. Now we have an example. Calculate the overall order of reaction which has the rate expression A rate equal to K A raised to the power 1 upon 2 and B raised to the power 3 upon 2, and rate equals to, and B rate equals to K A raised to the power 3 by 2 and B raised to the power minus 1. Solution. Rate for A, rate equals to, we know rate equals to K a raised to power x and b raised to power y, and we know that order equal to x plus y, so order will be 1 by 2 plus 3 by 2, that is 2, so it is a second order. And for b, we know order equal to x plus y, so order will be 3 by 2 upon minus 1, which will be 1 by 2, so it is a half order. A balanced chemical equation never gives us a true picture of how a reaction takes place, since rarely a reaction gets completed in one step. The reaction taking place in one step are called elementary reaction, when a sequence of elementary reactions called mechanism give us the reaction are called complex reactions. This may be consecutive reaction, that is oxidation of ethane to CO3 and H2O passes through a series of intermediate steps in which alcohol, aldehyde and acid are formed. Reverse reactions and side reactions, that is nitration of phenyl yields orthonitrophenol and paranitrophenol. Unit of rate constants. For a general reaction, small a capital A plus small b capital B gives us small c capital C and small d capital D. Rate equals to a rate equals to k a raised to power x and b raised to power y, where x plus y equal to n, which is order of reaction, and we know that k equal to rate upon a raised to power x divided by a raised to power x and b raised to power y, which is equal to concentration by time into 1 upon concentration raised to power n, where a equals to b. Taking SI unit of concentration mole liter inverse and time as the unit of k for different reaction orders are listed in table 3.3. For zero order reaction, order is 0, so its unit will be mole liter inverse second inverse. And for first order reaction, where order is 1, so the unit of rate constant will be mole liter inverse by second multiplied by 1 upon mole liter inverse. So mole liter inverse and mole liter inverse will be cancelled out, so the unit will be S inverse. And for second order reaction, where order is 2, so the unit of rate constant is mole liter inverse by second multiplied by 1 upon mole liter inverse raised to power 2, so the rate will be mole inverse liter second inverse. Molarity of a reaction. Another property of a reaction called molarity helps in understanding its mechanism. The number of reacting species, atom signs or molecules taking part in an elementary reaction which must collide simultaneously in order to bring about a chemical reaction is called molecularity of a reaction. The reaction can be unimolecular when one reacting species is involved, for example decomposition of ammonium nitrate. NH4NO2 gives us N2 plus 2H2O. Bimolecular reactions involve simultaneous collision between two species. For example, dissociation of hydrogen iodide. 2HI gives us H2 plus I2. Trimolecular or termolecular reactions involve simultaneous collision between three reacting species. For example, 2NO plus O2 gives us 2NO2. The probability that more than 3 molecules can collide and react simultaneously is very small. Hence, reactions with the molecularity 3 are very rare and slow to proceed. It is therefore evident that complex reactions involving more than 3 molecules in the stoichiometric equation must take place in more than one step. This reaction, which apparently seems to be the of 10th order, is actually second order reaction. The reaction is KClO3 plus 6 FeSO4 plus 3 H2SO4 gives us KCl plus 3 Fe2 SO4 whole thrice plus 3 H2O. This shows that the reaction takes place in several steps, which steps control the rate of the overall reaction. The question can be answered if we go through the mechanism of reaction. For example, chances to win the relay race competition by a team depends upon the slowest person in the team. Similarly, the overall rate of reaction is controlled by the slowest step, which is called the rate determining step or RDS. Consider the decomposition of hydrogen peroxide, which is catalyzed by iodide ion in an alkaline medium. 2H2O2 in alkaline medium gives us 2H2O plus O2. The rate equation for this reaction is found to be rate equals to minus dH2O2 upon dt equals to KH2O and I minus. This reaction is first order with respect to both H2O2 and I minus. Evidence suggests that the reaction takes place in two steps. H2O2 plus I minus gives us H2O plus IO minus, and H2O2 plus IO minus gives us H2O plus I minus plus O2. Both the steps are bimolecular elementary reactions. Species IO minus is called as an intermediate since it is formed during the course of the reaction but not in the overall balanced equation. The first step being slow is the rate determining step. Thus, the rate of formation of intermediate will determine the rate of this reaction. Thus forms the discussion till now. We conclude the following. Order of reaction is an experimental quantity. It can be 0 and even a fraction, but molecularity cannot be 0 or a non-integer. Order is applicable to elementary as well as complex reaction, whereas molecularity is applicable only for elementary reactions. For example, for complex reactions, molecularity has no meaning. For complex reactions, order is given by the slowest step, and the molecularity of the slowest step is same as the order of the overall reaction. Now we will discuss about integrated rate equations. We have already noted that the concentration dependence of rate is called differential rate equation. It is not always convenient to determine the instantaneous rate, as it is measured by determination of slope of the tangent at point t in concentration versus time plot. This makes it difficult to determine the rate law and hence the order of the reaction. In order to avoid this difficulty, we can integrate the differential rate equation to give a relation between directly measured experimental data, that is concentrations at different times and rate constant. The integrated rate equation are different for the reactions of different reaction orders. We shall determine these equations only for 0 and first order chemical reactions. Now we shall discuss about zero order reactions. Zero order reaction means that the rate of the reaction is proportional to 0 power of the concentration of reactant. Consider the reactant gives product, and rate equals to minus dr upon dt kr raised to power 0. As any quantity raised to power 0 is unity, so rate equals to minus dr upon dt equals to k into 1. So dr will be minus k dt. Integrating both sides, we get r equals to minus kt plus I, where I is the constant of integration. At t equals to 0, the concentration of the reactant r equals to r naught, where r naught is initial concentration of the reactant. Substituting in equation 3.5, which is r equals to minus kt plus I, so we get r naught equals to minus k into 0 plus I. So r naught equals to I. Substituting the value of I in the equation, r equals to minus kt plus r naught, and comparing with equation of a straight line y equal to mx plus c, if we plot r against t. Comparing this equation with equation of straight line y equals to mx plus c, if we plot r against t, we get a straight line with slope equals to minus k and intercept equal to r naught. Further simplifying equation 3.6, we get the rate constant k as k equals to r naught minus r upon t. Zero order reactions are relatively uncommon, but they occur under special conditions. Some enzyme catalyzed reactions and reactions which occur on metal surface are a few examples of zero order reactions. The decomposition of gaseous ammonia on a hot platinum surface is a zero order reaction at high pressure. 2NH3 at gaseous state equals to at 1130 Kelvin, and palladium and platinum catalyst gives us N2 and 3H2, and the rate is zero order. In this reaction, platinum metal acts as a catalyst. At high pressure, the metal surface gets saturated with gas molecules, so a further change in reaction conditions is unable to alter the amount of ammonia on the surface of the catalyst, making rate as a reaction independent of its concentration. The thermal decomposition of Hi on gold surface is another example of zero order reaction. Now we shall discuss about first order reactions. In this class of reactions, the rate of the reaction is proportional to the first first power of concentration of the reactant R. For example, rate gives product rate equal to minus dr upon dt equals to kr, or dr upon r equals to minus k dt. Integrating this equation, we get ln r equals to minus kt plus I, where again I is the constant of integration and its value can be determined easily. When t equals to 0, r equals to r naught, where r naught is the initial concentration of the reactant. Therefore, this equation can be written as ln r naught equals to minus k multiplied with 0 plus I. So ln r naught equals to I. Substituting the value of I in equation 3.8, we get ln r equals to minus kt plus ln r naught. Rearranging this equation, we get ln r upon r naught equals to minus kt, or k equal to 1 upon t ln r naught upon r. At time t1 from equation, we get ln r1 equals to minus kt 1 plus ln r naught. At time t2, we get ln r2 equals to minus kt2 plus ln r naught, where r1 and r2 are the concentration of the reactants at time t1 and t2 respectively. Subtracting this equation from subtracting ln r2 equals to minus kt2 plus ln r naught from ln r1 equals to minus kt1 plus ln r not, we get ln r1 upon r2 equals to k t2 minus t1, and k equals to 1 upon t2 minus t1 ln r1 upon r2. This equation can be written as ln r upon r naught equals to minus kt, taking antilog on both sides r equals to r naught e raised to power minus kt. Comparing this equation with y equal to mx plus c, if we plot ln r against t, we get a straight line with slope minus k and intercept equal to ln r naught. The first order rate equation can also be written in the form k equal to 2.303 by t log r naught upon r, or log r naught by r equal to kt divided by 2.303. If we plot a graph between log r naught by r versus t, the slope equals to k upon 2.303. Hydrogenation of ethane is an example of first order reaction. All natural and artificial radioactive decay of unstable nuclei take place by first order reactions. Let us consider a typical first order gas phase reaction A equals to B plus C. Let P1 be the initial pressure of A and Pt be total pressure at time t. Integrated rate equation for such a reaction can be derived as total pressure Pt equals to Pa plus Pb plus Pc pressure units. Pa, Pb and Pc are the partial pressures of A, B and C respectively. If X atm be the decrease in pressure of A at time t and 1 mole each of B and C is being formed, the increase in pressure of B and C will also be X atm each. At time t equals to 0, A gives B plus C, P1 atm, 0 atm and 0 atm, and at time t, Pi minus X atm for A and X atm for B and X atm for C, where Pi is the initial pressure at time t equals to 0. Pi equals to Pi minus X plus X equals to Pi plus X, and X equal to Pt minus Pi, where P equal to Pi minus X and Pi whole bracket Pt minus Pi, or which is equal to 2 Pi minus Pt. Hence k equal to 2.303 t log Pi upon Pa equals to 2.303 log Pi equal to 2 Pi minus Pt. The following data. Now we shall read about half-life of a reaction. The half-life of a reaction is the time in which the concentration of a reactant is reduced to 1/2 of its initial concentration. It is represented as T1 upon 2. For a zero order reaction constant, a rate constant is given by k equal to r naught minus r upon t. At t equals to t1 by 2, r equal to 1 upon 1 by 2 r naught, the rate constant at t1 upon 2 becomes k equal to r naught minus 1 upon 2 r naught divided by t1 by 2. t1 by 2 equals to r naught upon 2k. It is clear that t1 by 2 for a zero order reaction is directly proportional to the initial concentration of the reactants and inversely proportional to the rate constant. For the first order reaction, k equals to 2.303 by t log r naught upon r. At time t equals to 1 by 2, r equal to r naught by 2. So the above equation becomes k equals to 2.303 t1 by 2 log r naught divided by r by 2, or t1 upon 2 equals to 2.303 by k log 2. T1 by 2 equals to 2.303 by k into 0.301, or T1 by 2 equals to 0.693 upon k. It can be seen that for first order reaction, half-life period is constant, that is, it is independent of initial concentration of the reacting species. The half-life of first order reaction is readily calculated from the rate constant and vice versa. For zero order reactions, T half is directly proportional to R naught, that is the initial concentration of R naught. For first order reaction, T half is independent of R naught. Now, the table 3.4 gives us integrated rate laws for the reaction of 0 in first order. Order 0. Reaction type, reactant gives product. Differential rate law, dr upon dt equals to minus k. Integrated rate law, kt equals to r naught minus r. Straight line plot, r versus t. Half-life, r naught upon 2k. Units of k. Concentration, time inverse, or mole, liter inverse, second inverse. Now order 1. Reaction type, reactant gives product. Differential rate law, dr by dt equals to minus kr. Integrated rate law, r equals to r naught e raised to power minus kt, or kt equals to ln r naught by r. Straight line plot, ln r versus t. Half-life, ln 2 divided by k, units of k, time inverse or second inverse. The order of a reaction is sometimes altered by conditions. There are many reactions which obey first order rate law, although they are higher order reactions. Consider the hydrolysis of ethyl acetate, which is a chemical reaction between ethyl acetate and water. In reality, it is a second order reaction, and concentration of both ethyl acetate and water affect the rate of reaction, but water is taken in large excess for hydrolysis. Therefore, concentration of water is not altered much during the reaction. Thus, the rate rate of reaction is affected by concentration of ethyl acetate only. For example, during the hydrolysis of 0.01 mole of ethyl acetate with 10 mole of water, amount of the reactants and products at the beginning T equals to 0 and completion T of the reaction are given as under CH3COO C2H5 plus H2O gives us CH3COOH plus C2H5OH, and for time t equals to 0 the concentration of CH3COO C2H5 is 0.01 mole, and for H2 it is 10 mole, and for CH3COOH it is 0, and for C2H5OH it is as well as 0. And at time equals to t the concentration is CH3COO C2H5 0 mole, H2O 9.99 mole, CH3COOH is 0.0 mole, 0.01 mole, C2H5OH is 0.01 mole. The concentration of water does not get altered much during the course of the reaction. So the reaction behaves as first order reaction. Such reactions are called pseudo first order reaction. Pseudo means fake. Inversion of cane sugar is another pseudo first order reaction. Now we shall discuss about temperature dependence of the rate of reaction. Most of the chemical reactions are accelerated by increase in temperature. For example, in decomposition of N2O5, the time taken for half of the original amount of material to decompose is 12 minutes at 50 degrees Celsius, 5 hours at 25 degrees Celsius, and 10 days at 0 degrees Celsius. You may also know that in a mixture of potassium permanganate KMnO4 and oxalic acid H2C2O4, potassium permanganate gets colorized faster at a higher temperature than at a lower temperature. It has been found that for a chemical reaction with rise in temperature by 10 degree, the rate constant is nearly doubled. The temperature dependence of the rate of a chemical reaction can be accurately explained by Arrhenius equation. It was first proposed by Dutch chemist J.H. van 't Hoff, but Swedish chemist Arrhenius provided its physical justification and interpretation. K equals to A e raised to power minus E upon RT, where A is the frequency factor or the where A is the Arrhenius factor or the frequency factor. It is also called pre-exponential factor. It is a constant specific to a particular reaction. R is a gas constant and EA is activation energy measured in joules per mole. It can be understood clearly using the following simple reaction. H2 plus I2 gives us 2HI. According to Arrhenius, the reaction can take place only when a molecule of hydrogen and a molecule of iodine collide to form an unstable intermediate. It exists for a very short time and then breaks up to form two molecules of hydrogen iodide. The energy required to form this intermediate called activated complex is known as activation energy. Is obtained by plotting potential energy versus reaction coordinate. Reaction coordinates represent the profile of energy change when reactants change into products. Some energy is released when the complex decomposes to form products, so the final enthalpy of the reaction depends upon the nature of reactants and products. All the molecules in the reacting species do not have the same kinetic energy. Since it is difficult to predict the behavior of any one molecule with precision, Ludwig Boltzmann and James Clerk Maxwell used statistics to predict the behavior of large number of molecules. According to them, the distribution of kinetic energy may be described by plotting the fraction of molecules with a given kinetic energy versus kinetic energy. Here, Ne is the number of molecules with energy E and Nt is total number of molecules. The peak of the curves corresponding to the most probable kinetic energy, that is kinetic energy of maximum fraction of molecules. There are decreasing number of molecules with energies higher or lower than this value. When the temperature is raised, the maximum of the curve moves to the higher energy value and the curve broadens out, that is spreads to the right such that there is a greater proportion of molecules with much higher energies. The area under the curve must be constant since total probability must be 1 at all times. We can mark the position of EA on Maxwell-Boltzmann distribution curve. Increasing the temperature of the substance increases the fraction of molecules which collide with energies greater than EA. It is clear from the diagram that in the curve at T plus 10, the area showing the fraction of molecules having energy equal to or greater than activation energy gets doubled, leading to doubling the rate of a reaction. In the Arrhenius equation, the factor E raised to power minus EA upon RT corresponds to the fraction of molecules that have kinetic energy greater than EA. Taking natural logarithm on both sides of equation, ln k equals to minus EA by RT plus ln A, the plot of ln k versus 1 upon T gives a straight line according to the equation. Thus it has been found from Arrhenius equation that increasing the temperature or decreasing the activation energy will result in an increase in the rate of reaction and an exponential increase in the rate constant. In figure, slope equals to minus EA upon R and intercept is equals to ln A. So we can calculate EA and A using these values. At temperature T1, ln K1 equals to minus EA upon RT1 plus ln A. At temperature T2, equation is ln K2 equals to minus EA by RT2 plus ln A. Since A is a constant for a given reaction, K1 and K2 are the values of rate constant at temperature T1 and T2 respectively. Subtracting equation 3.20 from 3.21, we obtain ln K2 minus ln K1 equals to EA by RT1 minus EA upon RT2. ln K2 by K1 equals to EA by R and multiplied by 1 upon 1 by T1 minus 1 upon T2. Log K2 by K1 equals to EA divided by 2.303 R 1 by T1 minus 1 upon T2. Log K2 by K1 equals to EA 2.303 R T2 minus T1 divided by T1 plus T1 T2. Now we shall discuss about effect of catalysts. A catalyst is a substance which increases the rate of reaction without itself undergoing any permanent chemical change. For example, MnO2 catalyzes for the following reaction so as to increase its rate considerably. 2KClO3 and the catalyst is MnO2, which gives us 2KCl plus 3O2. The word catalyst should not be used when the added substance reduces the rate of reaction. The substance is then called inhibitor. The action of the catalyst can be explained by intermediate complex theory. According to this theory, a catalyst participates in a chemical reaction by forming temporary bonds with the reactants, resulting in an intermediate complex. This has a transitory existence and decomposes to yield products in the catalyst. It is believed that the catalyst provides an alternate pathway or reaction mechanism by reducing the activation energy between reactants and products and hence lowering the potential energy barrier as shown in figure 3.11. It is clear from Arrhenius equation that lower the value of activation energy, faster will be the rate of reaction. A small amount of catalyst can catalyze a large amount of reactants. A catalyst does not alter Gibbs energy delta G of a reaction. It catalyzes the spontaneous reaction but does not catalyze non-spontaneous reactions. It is also found that a catalyst does not change the equilibrium constant of a reaction, rather it helps in attaining the equilibrium faster. That is, it catalyzes the forward as well as the backward reactions to the same extent so that the equilibrium state remains same but is reached earlier. Now we shall discuss about collision theory of chemical reactions. Though Arrhenius equation is applicable under a wide range of circumstances, collision theory, which was developed by Max Strauss and William Lewis in 1916 to 1918, provides a greater insight into the energetic and mechanistic aspect of reactions. It is based on kinetic theory of gases. According to this theory, the reactant molecules are assumed to be hard spare and reaction is postulated to occur when molecules collide with each other. The number of collisions per second per unit volume of the reaction mixture is known as collision frequency Z. Another factor which affects the rate of chemical reaction is activation energy, as we have already studied. For a bimolecular elementary reaction, A plus B gives us products. Rate of reaction can be expressed as rate equals to ZAB e raised to power minus E upon RT, where ZAB represents the collision frequency of reactant A and B, and E raised to power minus EA upon RT represents the fraction of molecules with energy equal to or greater than EA. Comparing with the Arrhenius equation, we can say that A is related to collision frequency. This equation predicts the value of rate constants fairly accurately for the reactions that involve atomic species or simple molecules, but for complex molecules, significant deviations are observed. The reason could be that all collisions do not lead to the formation of products. The collisions in which molecules collide with sufficient kinetic energy, called the threshold energy, and proper orientation so as to facilitate breaking of bonds between reacting species and formation of new bonds to form products are called as effective collisions. For example, formation of methanol from bromoethane depends upon the orientation of reactant molecules as shown in figure 3.12. The proper orientation of reactant molecules lead to bond formation, whereas improper orientation makes them simply bounce back and no products are formed. To account for effective collisions, another factor P, called the probability or steric factor, is introduced. It takes into account the fact that in a collision, molecules must be properly orientated. That is, rate equals to PZABE whole raised to power minus E upon RT. Thus, in collision theory, activation energy and proper orientation of the molecules together determine the criteria for an effective collision and hence the rate of chemical reaction. Collision theory also has certain drawbacks as it considers atoms molecules to be hard spheres and ignores their structural aspect. You will study details about this theory and more on other theories in your higher classes. So now we will head towards the summary of the chapter. This was all about our chemical kinetics. So chemical kinetics is a study of chemical reaction with respect to a reaction rate, effect of various variables, rearrangement of atoms and formation of intermediates. The rate of reaction is concerned with decrease in concentration of reactants or increase in the concentration of product per unit time. It can be expressed as the instantaneous rate at a particular instant of time and average rate over a large interval of time. A number of factors such as temperature, concentration of reactants, catalyst affect the rate of reaction. Mathematical representation of rate of reaction is given by rate law. It has to be determined experimentally and cannot be predicted. Order of reaction with respect to a reactant is the power of its concentration which appears in the rate law equation. The order of reaction is the sum of all such power of concentration for different reactions. Rate constant is the proportionality factor in the rate law. Rate constant and order of reaction can be determined from rate law or its integrated rate equation. Molecularity is defined only for an elementary reaction. Its values are limited from 1 to 3, whereas order can be 0, 1, 2, 3, or even a fraction. Molecularity and order of an elementary reactions are same. Temperature dependence of rate constant is described by Arrhenius equation. K equals to A e raised to power minus E upon RT, and EA corresponds to activation energy and is given by the energy difference between activated complex and the reactant molecules, and A, Arrhenius factor or pre-exponential factor, corresponds to the collision frequency. The equation clearly shows that increase of temperature or lowering of EA will lead to an increase in the rate of reaction, and presence of catalyst lowers the activation energy by providing an alternate path for the reaction. According to collision theory, another factor P, called steric factor, which refers to the orientation of molecules which collide, is important and contributes to effective collision, thus modifying the Arrhenius equation to K equals to PZABA whole raised to power minus EA upon RT. So this was all for our chapter chemical kinetics. Thank you all for watching.